All right, the last of our video lectures for Chapter 1. This is 1.2b, and in this video lecture we're going to review the scientific method. Scientific method is an agreed upon systematic approach to scientific research or inquiry. Ultimately, as scientists, we all have to have a general way that we go about our research that covers everything we need it to cover and that progresses in a consistent way. And this is what we call the scientific method. Here are the basic 6 steps of the scientific method, and we're going to try to remember these through a silly analogy. And as science teachers, we're all going to try to use this same basic acronym. And so the acronym is People Really Hate Elephants Around Cars. And if you look at the picture above, you see all these. People, the first step is problem. Uh, Really, the second step is research. Hate is hypothesis. Elephants stands for experiment. The A in around stands for analysis, and the C in cars stands for conclusion. So it's kind of a silly analogy, but if it's easy enough to remember, it might help us not forget any of these steps or forget the order that they come in. So our first step, problem. This is the issue that we have. This is the question that we would like to be answered, the problem we would like to be solved. And we wouldn't know about this unless we really started with observation. So in a way, observation is a kind of a pre-step to the whole scientific method. It's something that piques our interest. We observe something, and because we observe it, especially as a young child, we always ask the question, why does that happen? What is that? And so we see something. Often it's through our sight, but we have an observation, and that leads us to a question. And then those questions often lead to more detailed, better observations. And then eventually we come up with the question or problem. We say, this is what we want to have solved or answered. And once we get to that point, it's important, and this is at the very bottom here and underlined, we need to make sure that our problem or our question is able to be tested. If it's not able to be tested, then we really can't base any research around it, or we can't perform real science around it. But if it is testable, we also need to make sure that it is logical and it's relevant. It needs to be logical in the sense that it is worthwhile to spend time and money researching, and it also needs to be relevant within your social construct. And so we need to make sure that our problem or question is worthy of doing research on. Well, once we decide what our question or problem is, we need to know a little more background information about it. Now, hopefully when you go to do this, you already have some background information, but we still have to research more about that. And so this gives us a better feel for whatever we might be running our scientific experiment or research on. But we need to do the research. This is like the notes in class, and I know some of you feel a little bit like this gentleman here when you take notes. It's not exciting. It is the part that's not as enjoying, or doesn't bring you as much joy, but nonetheless, it is important. It's a huge step. And when you do research, you tend to find two different types of data. One is called quantitative, and in that you see the word, or you could imagine the word quantity. That's the root word there. And quantity refers to how much. So this is numerical information. And then in qualitative data, you could see the root word in there, quality. And the quality of something has to do with non-numerical information. It reveals properties about that data. So here we see a table, and feel free to look through all of it, but I want to highlight the very top bullet on each side. In qualitative data, it deals with descriptions. You are describing the data, and usually physically, possibly chemically. On the other side, quantitative data deals with numbers. It's all about numerical information. So once we've obtained our research, then we need to make a prediction or a guess on the question or problem. And this we know is a hypothesis. And you've heard this often called an educated guess. Notice that's not the definition I gave. Because an educated guess is exactly this, a possible explanation. It's testable, and it could be called a prediction, but it's based on observation and research. It is not a crystal ball guess. It's definitely not that. What it is an educated guess. Again, it needs to be based on our observations, based on our research, and it doesn't mean that it has to be correct or supported, but it does need to have some connection to the research that we've done. So that's why it always comes after that research step. Notice that it is supported but not proven. Doesn't matter if our experiment matches perfectly with a hypothesis, all it does is support the hypothesis. Because of course in science and in reality we cannot test every single variable or everything that could go into it, every possible explanation. So it only supports the question or problem. Once we figure that all out, then we run our experiment. And this is the fun part. This is the lab for us. We go in and we test that hypothesis, and we use variables in order to do that. And so a variable then is something that can change. And in math, we have constants and variables. Constants are locked in, they stay the same. Variables are things that can be manipulated or changed. So again, that's important to recognize a variable as something that can change. So when we talk about variables, there are two main types of variables. If we look at this example in the upper right hand corner in the picture, we could look at how light affects plant growth. Well, as a person performing the experiment, there's a lot of things that I can change. I could change the type of plant, the type of soil, whether or not it gets fertilizer, the type of fertilizer, the amount of water, and the type and amount of sunlight. All of those are what we call independent variables. Those are all things that I, as the scientist, can directly change in the experiment. Now, the obvious end of this would be if I change these things, what would change as a result? And it would be how the plant grows. And so that's a dependent variable. I can't change directly how the plant grows. I can only change the conditions around the plant, which then will change how it grows. And so a dependent variable changes because of a change in the independent variable. And what we see here is kind of an if-then, cause and effect type relationship. The independent variable is the cause, it's what I change. The dependent variable is the effect, it's what changes as a result or because of. So if I change the type of soil, then the plant growth will be changed as a result. One other thing to mention here with experimentation is something we call a control group. Often when we're running experiments, if you run multiple trials, you want to compare them back to what might be considered the standard. So if I look at the light affecting plant growth, my standard might be 12 hours of natural sunlight and then 12 hours of darkness. And maybe I adjust the amount of light or adjust the type of light, but I always compare it back to that standard of 12 hours of natural sunlight and 12 hours of darkness per day on that plant. So that's what we mean by a control group. I don't think the picture really identifies it better, but it was funny. All right, so the A in this is analyzation. Once I run the experiment, I've got some information. And here again in analyzation, we are looking at data once again, but this is data from the experiment. And so now we're breaking down those results or that data. Again, could be qualitative or it could be quantitative data, but we are critically analyzing that. We're assessing it, we're looking at it. If it's quantitative data with numericals, sometimes we need to run some mathematics. Sometimes we need to maybe plot the information in a graph. That's in this step. If it's not quantitative information, if it's not numerical, sometimes we need to look at those properties and compare them back to that research that we did and kind of lay them on top of each other to figure out if the properties or the descriptions we find match our background information. And so all of this is leading us eventually to drawing that conclusion. But this is a step on its own of working with our results from the experiment. Sometimes this happens very quickly. Sometimes this step may take a lot of time. Obviously that depends on the experiment. Last step of the scientific method is our conclusion, the same as the last thing you would do in a research paper or an English paper. This is the final end of it. In our lab reports, the conclusion is really important. It's really summing everything up, but it's going back to this idea of being a judgment based on the analyzation. So we take our information from the experiment, we analyze it, and we make our own judgment in relation to the hypothesis. Remember, it's stating whether the hypothesis is supported or not, and sometimes we say supported greatly or weakly because support may vary, and it always leads the way to more experimentation. One conclusion on one experiment is almost never enough. There's always room for more experimentation. When you write your conclusions in your lab report, we should always include the route we would take to further our research, to do more experimenting. The last part of the scientific method I want to mention isn't one of these 6 steps, but it is an important part, and this is the lab report that I was referring to. After we get all this information, we have to communicate it to other scientists or to the general public or to your science teacher. And this is an organized way about doing it. And it's not magic. It takes a little work. You don't get to just funnel it through a magic funnel and then poof, it's on the paper. It takes a little work and it takes a little time to put into it. Now, through communicating results, there's 2 things that could result in this. Most of us will never have any part in these, but theories and laws have been generated through scientific research over the years. A theory explains and a law describes. That's probably the most important thing for you to realize here is a theory explains and a law describes. Theories and laws are both generalizations. A theory is not proven, but is still used to predict. So it's used to look at what could happen if the theory itself is holding up. And a law is not going to explain the phenomena, it's just going to describe the reality of it. And there's 2 ideas that we can think of here. Obviously, gravity is not a theory, it's a law, and it's a law because we've never found there to be any exception to the law of gravity. But the law of gravity doesn't explain why or how it happens. It's simply just describing the constructs of the law, or describing the conditions of it. Now, if we think of theories, a theory of evolution is a common one. That theory is not actually describing it, it's explaining how it might actually be happening. And it's based on a lot of scientific evidence, but it doesn't mean that it's proven. And the theory of evolution might be used to predict how alligators possibly could change over time if they've evolved from other creatures. And so that gives us a basis for prediction. And again, the theory is used to predict. The law is just simply described and is much more concrete. So a lot of debate we can have with theories and laws, but that's the basic definition of the 2. And that is all for Chapter 1. Jump for joy.